All right, so moving on to section 5.3, what we are going to do in sections 5.3 through 5.6, beforehand, being able to tell if a sum converged seemed like a little bit of work, right? I've got to find the first sum and then the sum of my first two terms and then the sum of my first three terms, first four terms, blah, 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 and just kind of see what happens, right? Seems like a little bit of work. These are going to be tricks to really help us see what's happening without having to really do a whole lot of work. That's our point here. Another thing too, from now on, with a few exceptions, we don't really care what the sum is going to actually be, just that it has one. Okay, so like beforehand in section 5.2, we said like it has a sum of 2 or a sum of 10. We don't really care about that. We just want to know if it has one. That's so. So then that's what we are going to be doing here. Section 5.3, 5.4, 5.5, and 5.6. So section 5.3 has two tests. These are the divergence test and the integral test. The divergence test is my favorite one because it is quick and it is very hard. What this test says is if the limit as n goes to infinity of an is equal to c, and that c is not equal to 0, or if it does not exist, then it's going to diverge. So what does this mean? If the limit is something other than 0, it's going to diverge. Why does that make sense, right? Well, imagine if my terms are getting really close to c. This means I'm adding c every time. Plus c, plus c, plus c, plus c, which means it'll just grow and grow and grow and grow and grow. The only way my sum is going to get closer to a certain thing is if my terms are getting really close to 0, because then I'm going to add a bunch of smaller terms, right? So, example number 1, for each of the following, apply the divergence test. If the divergence test proves that it diverges, state that. But if not, then it is inconclusive. So, example 1a is the sum n equals 1 to infinity of n over 3n minus 1. So what I want to see is what's happening to my terms. So let's see what happens as n gets really big. Well, remember from Cal 1, I just want to look at the largest one for each part, right? So the largest term on top is the n. Largest term on the bottom is 3n. N's cancel out, so I'm left with a 1 on top and a 3 down here. So my terms are getting closer to 1/3, which means for the sum, I'm adding 1/3 a bunch of times, which means it'll just grow and grow and grow, plus a third, plus a third, plus a third, plus a third. It'll just grow and grow and grow. So this diverges by the divergence test. Diverges. For b, we're looking at the sum from n equals 1 to infinity of 1 over n cubed. Well, if I did that, the bottom is getting really small, which means the whole thing is getting the bottom is getting really big, which means the whole thing is getting really small. 0 there. Now, what this means is that the divergence test is inconclusive. The divergence test can only tell us if it for sure diverges. It doesn't let us know anything else. So it is inconclusive there. And then example C is the sum from n equals 1 to infinity of e to the power of 1 over n squared. So again, we're going to take the limit. e to the power 1 over n squared. As this gets really big, the whole thing gets really small, so that's e to the 0, which is 1. Which again means it's like I'm doing plus 1, plus 1, plus 1, plus 1, plus 1. So this diverges. So this is always a really good starting point, because if I already know it diverges, then I can just stop. I don't have to like do any more work, any more steps. From here right now, I can go ahead and stop. For this one, I've got to do a little bit more because it didn't help me, right? But if it diverges, I can just go ahead and stop. So that is the divergence test. Move on to the integral test. This says, suppose the sum of an is a series with positive terms an. Suppose there exists a function f and a positive n such that the following three are true. F is continuous, f is decreasing, and f of n is equal to an. Then the behavior of the sum and the behavior of the integral are the same. This is what we learned in section. I'm going to get this wrong. I think it was 3.8. The last one in chapter 3, we handled this. So since I know how to handle this, I can solve this instead, and it's going to tell me what's happening for the sum. So that's nice. So for example number 2, for each of the following, use this test to determine whether the series converges or diverges. First one's the sum from n equals 1 to infinity of 1 over n to the third. We just said the divergence test didn't help us here, so then I've got to try something else now, right? So what I'm going to do is I want to look at the integral from 1 to infinity of 1 over n to the third. So we learned this a while back, right? This we can't do, so we're going to have to do the limit as t goes to infinity, 1 to t. This is like saying n to the negative third, dn. So add 1 to the power gives us negative 2. Divided by that power is going to give us negative n to the negative 2 over 2 from 1 to t. Plug in a t, and that's like saying t to the negative 2, which is 1 over t squared, so negative 1 over 2t squared. Minus makes it plus. Plug in a 1, we just get 1, so 1 half. Plug in infinity in for the t. The bottom is really big, which makes the whole thing really small, which means this converges to 1 half. Since this converges, so does this. We don't know what it converges to. We just know it's going to converge. Example B, we're doing the same thing. Sum from n equals 1 to infinity of 1 over the square root of 2n minus 1. So let's do the same thing. Integral from 1 to infinity, 1 over square root 2n minus 1. That's going to be the limit as t goes to infinity of the integral from 1 to t. This is 2n minus 1 to the negative 1 half. Whoa. Negative 1 half. Use u substitution here. U equals 2n minus 1. So du is going to be 2 dn. I don't have a 2, so put 1 half out front. 1 half, limit t to infinity. Plug in a 1 right here. 2 times 1 is 2, minus 1 is 1. And this would be 2t minus 1. U to the negative 1 half du. Add 1 would be a half. Divided by a half is like saying times 2, so it's going to cancel out with this half. So that's going to end up being u to the 1/2 from 1 to 2t minus 1, the limit of that. That's going to be the limit as t goes to infinity. 2t minus 1 to the 1/2 is like saying the square root of 2t minus 1. Minus, plug in a 1, the square root of 1 is just 1. As t gets really big here, the square root gets really big. So this whole thing gets really big, which means it diverges. It diverges. Example C, let's do the same thing for example C. Sum from n equals 1 to infinity of n over 3n squared plus 1. Let's do the same thing. Integral from 1 to infinity of n over 3n squared plus 1. Take the limit and replace it with t. Again, use u substitution. U equals 3n squared plus 1. So du would be 6n dn. I don't have a 6, so put 1/6 out front. Plug in a 1. 1 squared is 1. 3 times 1 is 3. Plus 1 is 4. Plug in a t. 3t squared plus 1. 1 over u du. The antiderivative of 1 over u is the natural log. So limit as t goes to infinity. Natural log, absolute value of u from 4 to 3t squared plus 1. So that's going to be 1/6 limit t goes to infinity of natural log 3t squared plus 1 minus natural log of 4. As t gets really big, this whole thing gets really big. So this is equal to infinity, which means this series is going to diverge. Does it make sense? Let me know. So using this idea, we can talk about a new type of series called the P series. What this is whenever I look like the sum of 1 over n to the p. When I look like the sum of 1 over n to the p, if p is greater than 1, it's going to converge. If it's less than or equal 1, I'm going to diverge. Let's think about why. So for 2a, I had 1 over n to the third. So when I take the antiderivative of that, it's going to be n to the -2, which is still in the denominator. So as n gets really big, this whole thing gets really small. Whereas, like in example C right here, I had 1 over u to the first, which gave me the natural log, which is going to just grow and grow and grow and grow and grow. So I diverged. Same thing with example number B. I had 1 over u to the 1/2, which meant I brought it up to u to the 1/2 over 1/2, which again made this diverge. So if the power in the denominator is greater than 1, converge. If it's less than 1, diverge. So for example 3a, it's 1 over n to the fourth, right? 4 is greater than 1, so this is going to converge. Whereas 1 over n to the 2/3, this is less than a 1, so this is going to diverge. If any of that does not make sense, let me know.